Okay, so welcome everyone to the one seminar. We're very happy to have Yury speak this week. So Yury is currently in EPSLC in Cambridge. Before that, he was funded by the Royal Society, also at Cambridge. He's done several postdocs in Munster, Lübeck, and Barron University. He was his PhD originally from Moscow State University. So we're very happy to have Yury speak this week. He's going to talk to us about approximation properties of two-layer neural networks with values in a Banach space.
Thank you very much for the introduction. Thank you very much for the invitation to both the One World Mathematics of Machine Learning seminar and the Isaac Newton Institute program on mathematics of deep learning. So as Matt already said, I will be talking about neural networks with values in a Banach space, so vector-valued neural networks. And I will be talking about what are the functions that they can approximate well. Okay, the structure of my talk is very simple. I'll start with an introduction in about the scalar valued case, so neural networks with values in R. And I will continue with my contribution, which is about vector-valued neural networks. And well, especially it's essentially it's a generalization of the scalar valued results by many people to the vector valued case. Okay, a nice disclaimer that I heard Matt do once: new talk, new typos. This is actually the second time I give this talk, but I'm sure there are enough typos to be found. So I encourage everyone to challenge me on that. Okay. To set the notation, you probably all know this already. What is a two-layer neural network? It's just the sum of some coefficients AI times a nonlinearity sigma applied to a scalar product of x with some vector bi plus a bias ci. These vectors bi are referred to as weights. They are in some space Rd, the input space of the network. The CIs are referred to as biases. Sigma is the activation function or the nonlinearity. These constructions here, sigma of the scalar product plus the bias, are called neurons, and collectively they constitute the hidden layer of the network. And these coefficients AI constitute the second or last layer of the network. And these brackets here denote the scalar product in Rd. Okay, there are famous universal approximation theorems that say that if sigma is not a polynomial, then any continuous function on a compact set can be approximated uniformly by two-layer neural networks of the form on the previous slide. But getting approximation rates is trickier. In general, even if the underlying function is Lipschitz, the rates will be bad. They will be exponential in the dimension of the input space D. So the error would scale like O of n to the minus 1 over D. If D is large, it's basically order 1. However, for special classes of functions, there are Monte-Carlo rates order 1 over square root of n can be achieved. And the first type of these functions was found by Barron in 1993. These functions, so the class of these functions will be called the Barron class. And it's all functions from Rd to R such that their Fourier transform, so f is the modulus, the magnitude of the Fourier transform of the function f. If it's the case sufficiently fast, so that omega times f of omega converges and is bounded by some constant c, then Barron has shown that for any function that satisfies this assumption, there exists, and for any n, there exists a two-layer neural networks of the form we had on the previous slide with at most n neurons, such that the neural network approximates the function f from the Barron class in the L2 norm on any bounded compact set B in RD with a Monte-Carlo rate. So the approximation error is less than 2c, where c is this constant here, over square root of n. And we will remember this for later. And also important, the weights of the second layer, of the outer layer, these AIs, they can be chosen to satisfy this inequality here. So their L1 norm, small L1, will be bounded uniformly in n. And of course, these AIs will change depending on n, but still the sum will be bounded uniformly in n, and this bound only depends on this constant c, and this constant c is sometimes referred to as the spectral Barron norm. Okay, some remarks on this Barron class. This result by Barron assumes that sigma is sigmoidal, but it can also be extended to ReLUs, so this result also holds for ReLUs. However, all functions in the Barron class, because of that fast decay of the Fourier transform, are C1, so piecewise affine functions are not in that Barron class. But they clearly can be efficiently approximated by neural networks with ReLU activations. So the Barron class is a bit too small. There are more functions that can be efficiently approximated by two-layer neural networks than those that satisfy this spectral condition. And therefore, people started considering infinitely wide two-layer neural networks. So they replaced the sum that we had on the first slide with an integral over some compact topological parameter space. So now we just integrate these neurons, these sigmas of scalar product x with b plus c. We integrate it with respect to a measure a on a parameter space in over b and c. And A is a signed random measure. Typically, this parameter space A will be a unit ball in RD plus 1, where RD is the input dimension, so that's the dimension of this B here, and the 1 comes from the bias here. And the definition that Bach gave in 2017 to the space of functions that can be written in this form is the following one. Let's consider the space of functions that can be written in this integral form, and let's equip it with a norm that basically it's the Radon norm of this measure A. And we take, since the representation is not unique, we take the infimum over all such Radon measures such that the representation exists. And this we will call the variation norm, F or F1 norm. And the space will be called the variation norm space. Now, this space is also known under various different names, and different people have looked at it from slightly different angles and have obtained different results. So Bach called them variation norm spaces. Ehman, Wu, and Ian Wojtowicz have called them Barron spaces, and this shouldn't be confused with the Barron class or the spectral Barron class. There is also work by Onge, Sodry, and Srebro, and Parchi and Novak, where they call similar spaces the Radon BV2 spaces. There is also recent work by Bartolucci, De Vito, Rosasco, and Vigogna, where they look at these spaces from the reproducing kernel Banach space viewpoint, and there are also similar results coming from the Mieldt field approach to two-layer neural networks, papers by Rostkopf, Van den Eyden, and May, Mantanhari, and Nguyen, Shizate Bach, and Serignano, and Spiliopoulos. There are many more, but that's just a selection that I could fit into the slide. Okay, now another way of looking at two-layer neural networks, and the one that we will find useful later, is to write them down in the form of a linear-nonlinear decomposition. What I mean by that is if the neural network goes from RD to R, so this X is in RD, we apply a linear transformation B to it that goes from RD to Rn, and n is the number of neurons. We apply we add the vector of biases in Rn, then we apply, so that's the linear or the affine part. Then we add a nonlinearity, and then we apply another linear transformation again. And this transformation now goes from Rn to R. That's the last layer of the network. Now that's in the case of a finite width neural network. And the similar construction was first proposed, or at least that's where I first saw it, in a paper by Ye and Wojtowicz, where they replace this Rn here with the space of continuous functions over Rd. I think this d plus one is one of those typos that Matthew was afraid of. So they replace this Rn with the vector of continuous functions over Rd. So you have sort of infinitely many neurons, if you wish, and then the bias is also considered a continuous function on Rd, and then A is a linear operator that goes from these continuous functions to R. And if sigma is a positively one homogeneous activation like the ReLU, then the parameters can be also chosen on the unit ball in Rd, not on the whole space, and the magnitude can be taken out to this operator A. And in this case, the parameter space will be just the unit ball in Rd rather than the whole space, and the space of continuous functions will be also on the unit ball. Okay, and this is a viewpoint that we will find very useful in the second part of the talk. But now, let's see how this connects to the variation norm. Again, we consider a linear-nonlinear decomposition of a neural network. Now this operator B goes from Rd to the space of continuous functions over the parameter space. And A goes from the space of continuous functions to R, so it can be identified. It is a linear function since it goes to R. It's a linear function on the space of continuous functions over this unit ball. So it can be identified with a radon measure, A. And then again, we have such a representation of F used with a radian measure. Now these brackets denote the duality pairing between the space of continuous functions and the space of radon measures. And again, the F1 norm of a function F is given by the infimum over all such representations. And the infimum is of the radon norm of this measure A. Okay. So now these spaces, the main interest in these spaces is that these are the spaces where that contain the functions that can be efficiently approximated by two-layer neural networks. And here's the theorem on direct approximation from a paper by Ma and Wu in 2019. They say let mu be a probability measure on Rd with p greater than 1 finite moments, and let f be a function from that variation norm space on the whole space Rd. Then for any number n, there exists a two-layer neural network Fn with at most n neurons, such that again we have an approximation rate in the L2 norm. Well, L2 with respect to this measure mu that we had here. And again, the bound that we have is 2 norms of f over square root of n. And if you remember the bound in the Barron class, we had exactly the same estimate, but with the spectral Barron norm c. And again, we have an L1 type of bound on the coefficients, ai and the weights bi. And this is again bounded by the constant 2 times the f1 norm of the function f. And inverse approximation also holds. Inverse approximation means in that context that any function that can be any function that can be written as a finite with two-layer neural networks will converge to a function from this f1 space in a suitable sense as the number of neurons in the representation goes to infinity. Okay, so that concludes the introduction, and what I want to do now is to extend these results from neural networks with values in R to neural networks with values in an arbitrary Banach space. So first of all, generalizing it from R to some RK is, of course, very trivial, because you can just take k different neural networks that map to different components of RK. But in the case of an arbitrary Banach space, this is actually not trivial. Are there any questions so far before I continue? No. Okay. Okay. There has been quite a lot of work on learning in infinite dimensional spaces. Perhaps the first paper is this one by Michel and Pontil on learning vector-valued functions. This is in the context of Hilbert spaces, and so the output space or the target space is a Hilbert space. Then there is a paper by Zhang and Zhan on reproducing kernel Banach spaces, on vector-valued reproducing kernel Banach spaces. And there exists a good review by Alvarez, Rodasco, and Lawrence on kernel methods for vector-valued functions. So it's a good overview of what had been done. And also, recently, Nelson and Stewart considered the random feature model, which is shown to be equivalent to reproducing kernel Hilbert space approach. And this random feature model was studied for input-output maps between Banach spaces. And they also considered applications to partial differential equations. And apparently, well, the paper that is closest to what I wanted to do is this by Zhang and Zhang, where they consider vector-valued reproducing kernel Banach spaces, and these F1 spaces can actually be seen as a certain type of reproducing kernel Banach spaces, as that recent paper I cited has shown. But there are no convergence rates or anything like that for variation norm spaces in the vector-valued case. So this is what this is the purpose of this talk. Okay, so now we will use this linear-nonlinear decomposition to generalize these two-layer neural networks to an arbitrary output space Y. The form remains exactly the same. Now X is in some Banach space X, and the output space is some Banach space Y. What we want to have, we want them to have separable pre-duals. This will be needed to handle some duality between different operator spaces based of nuclear operators and linear bounded operators. Now sigma, we need to see what we mean by this nonlinearity in some Hilbert, in some Banach space, and we will understand this sigma as a sort of generalized ReLU function that we will define using partially ordered spaces, also called vector lattices, and it will be the lattice operation of taking the positive part. And now A, B, and C are yet to be defined, and we will also slightly abuse the notation, as many people do in the community. We will augment the input space X with another component in R. So this component reflects this bias C here, and the operator, we will consider this pair B and C as an operator acting on the scale on the Cartesian product of X and R, and it takes X and alpha to be X plus alpha C. And for inputs of the form X and 1, the two formulas are exactly the same. So from now on, we will forget about the C and just use this notation. Okay, Now, a short recap on partial order. People who have heard my talks before, they know that I almost always have this slide. So a partial order on some set S is a reflexive, antisymmetric, and transitive binary relation. So it's a subset of the Cartesian product of S with itself. Now, if you have a vector space X and it also has a partial order, and linear operations agree with the order operations in a very natural way. So if you add something, then the order does not change, or if you multiply by positive constants, the order doesn't change either. And in this case, this X, this vector space X with the partial order is called an ordered vector lattice. Sorry, ordered vector space. And if this space is a lattice, that means that every pair of elements have a uniquely defined supremum and infimum in the sense of that partial order. Then the whole thing is called a vector lattice or a Riesz space. And also using suprema and infima, we can define the concepts of a positive part of an element, a negative part of an element, an absolute value of an element, and we also have a nice decomposition of each element into the difference of two disjoint positive elements. So this generalizes what you would naturally expect from a space Rn or from a space of continuous functions. This does it in some sort of a more general framework. Okay, some examples of these vector lattices. Sequence spaces LP with P between 1 and infinity are clearly vector lattices with partial order defined point element-wise. The space of signed radon measures is also a vector lattice with a partial order defined as measure mu is greater or equal than measure nu, if mu of A is greater than nu of A for any measurable subset. Oops, sorry. Now, if these measures have densities with respect to the Lebesgue measure, we can, well, any measure, in fact, we can also express the same relation pointwise everywhere. The spaces, if the functions are continuous or even Lipschitz, we can define partial order pointwise, and perhaps less usual example is the space of functions of bounded variation on an interval, where we say that f is greater than g if and only if the difference is a non-decreasing function. You can think of the distributional derivative of a BV function on an interval, and then just consider the ordering between the derivatives which are radon measures. This will give you basically the same thing. Another example is the space of linear operators between two partially ordered spaces, where we order the operators by saying that A is greater than B if for any positive element x, it holds that AX is greater than BX. And this is a different order from the more commonly used semi-definite partial order. So for example, for matrices, it would be that A is greater than B if the difference is positive semi-definite. And this is indeed a partial order, but it is not a lattice because we will not have unique suprema and infima. Okay.
So the last one, I guess, partial ordering on your space X as well.
Sorry, for what?
For the last example, you have a partial ordering on space X.
Yes. So it's a space of linear operators that act between two partially ordered spaces. You need an ordering in X and also an ordering in Y. Yeah. Okay. Okay, now we can be more precise about what we mean by these vector-valued two-layer neural networks. We have this linear-nonlinear decomposition, A applied to sigma of Bx. X and Y will have separable preduals, and Y is also a vector lattice. So it has operations of pointwise operations of taking the positive part and the negative part defined in it. And sigma will be the generalized ReLU function, which will take an element y and return its positive part in the lattice sense. Now this operator b, it used to map between x and c on the continuous functions on the unit ball in RD. Now it maps into the continuous functions on the unit ball in the space of linear bounded operators from x to y, and these continuous functions are also y valued. And this operator will act as follows. It will take an x and map it to a linear operator that just evaluates any operator k at x. So it takes in an operator k and gives out kx. And now the operator a maps from this space of vector valued continuous functions on the unit ball in the space of linear operators to y, and it maps any function phi to this vector valued integral here, phi of k dA of k. And a is again a radon measure, a scalar valued signed radon measure on the unit ball in the space of linear operators from x to y. And the whole, well, this operation here is, it can be thought of a vector valued measure, and this would be the sort of the density of the measure. If you think of a polar decomposition of the measure, this would be the scalar part of it. Okay. So this is more or less what we want to do. This is just a generalization, even if it's a bit bulky, it's rather straightforward. But we need to make sense of all these things. So there are many caveats to this construction that we defined here. First of all, the parameter space is now not the unit ball in RD, but it's a unit ball. It's the unit ball in a space of linear bounded operators from x to y. And remember, we wanted a compact parameter space because we use duality between continuous functions and radon measures. So we need to make sure that if we want this unit ball to be compact, we need to make sure that the space of linear operators is a dual space, so it has a pre-dual, and then we can use the weak star topology. And then by the Banach-ReLU theorem, the unit ball will be compact. And indeed, there are general results from theory of tensor products of Banach spaces that say if x and y have separable pre-duals, and either x or the pre-dual of y has the approximation property, then the dual of the space of nuclear operators can be identified with the space of bounded operators. So in other words, the space of bounded operators has a pre-dual. And then by the Banach-ReLU theorem, the unit ball in the operators in the space of linear operators from L to Y is weakly star compact and also metrizable. So that's caveat number one. Now caveat number two, since we equip the unit ball in the space of linear operator with its weak star topology, we need to make sure that all the functions involved remain continuous, because we wanted to have continuous functions and then use their duality with radon measures. And this evaluation function Lx that goes from the unit ball in the space of linear operators to y, it needs to be weakly star continuous where this weak star topology is on the unit ball. And this will be true if we also equip y with its weak star topology. That's why we needed a pre-dual, one of the reasons why we needed a pre-dual. And now another thing, if you remember, we have this nonlinearity here. We need to make sure that this nonlinearity does not take us out of the space of continuous functions. So it needs to be weakly star continuous. And this turns out to be very restrictive for the ReLU, at least. Because, well, these lattice operations, they have been studied quite extensively. And there are general results that say that sequence spaces LP with P greater than 1 and Lipschitz spaces, the spaces of Lipschitz functions, have weakly star continuous lattice operations, but all other spaces we might be interested in, such as Lebesgue spaces with non-atomic measures of space of linear operators, in space, except in special cases, or the space of Radon measures, unless on discrete sets, they all don't have weakly star continuous lattice operations. So the operation of taking the positive part will destroy the continuity. And this is rather restrictive because we cannot use these ReLU type of functions in all these interesting spaces here below. Okay, now a third caveat, we can, using these constructions, these dualities between continuous functions and Radon measures, we can prove things like pointwise convergence, but if we want to obtain convergence rates in Bochner spaces, we somehow need to have a metric. So we need to metrize the weak star topologies we have in Y, for example, in the target space. And there is a standard way to metrize the weak star topology on a unit ball of dual space Y. And this can be done using this metric shown here. It's a sum, it's a weighted sum, weighted by 2 to the minus I, of these dual pairings with pre-dual elements eta I. And since the pre-dual is separable, as we assumed, there will be a countable dense system of these eta I's in the pre-dual. And then we normalize this distance again by 1 plus the same dual pairings. And if these eta I's are normalized, then we can also use an equivalent metric that only includes the dual pairings in the numerator, and the denominator can be just got rid of. So we will use this D star metric to define a norm. We will take a completion of the space Y with respect to this weak star norm or weak star topology, and this will be our target space. So we will redefine the metric on Y. This can be an example where this arises rather naturally is if you think of the space of Radon measures and you think of the weak star topology on that space, and the positive cones, or the probability measures, scale probability measures, they will be closed under taking weak star limits, but the whole space will not be. And if you take this completion, what you will get is something related to the Kantorovich-Rubinstein distance. You will get a space that has as its norm some metric that metrizes the weak star topology in the space of Radon measures. Okay, now with all these caveats, we can finally define vector-valued variation norm spaces. And the definition is exactly as before. Let X and Y be Banach spaces with separable preduals. Let Y be a vector lattice such that lattice operations are continuous, or indeed we need that they are also one Lipschitz with respect to the D star metric. Well, this one is of course irrelevant, but we need them to be Lipschitz, and it is restrictive because you can. It is more than continuity, obviously, because the Lipschitz constant will change depending on the ordering of these elements in the pre-dual of these eta I's that we use here. So anyway, we want lattice operations be one Lipschitz with respect to this weak star metric, and then we define the space of Y-valued variation norm functions as the space of all Lipschitz functions on X, such that this variation norm is finite, and the variation norm is, as usual, the infimum of the Radon norm of A, and remember A is a scalar valued, over all representations of f in this form. And we can indeed write this pointwise because it can be shown that all these functions are Lipschitz, so we can actually define them as a subset of the space of Lipschitz functions. Okay, and now we have Monte-Carlo rates in these vector valued F1 spaces, and the theorem is more or less the same as in the scalar valued case. Let all these above assumptions be satisfied, and let f be a vector valued F1 functions, variation norm function, and then for any n, there exists a 2-layer neural network with at most n neurons, and it will have the form, this following form here: alpha i's are coefficients, k i's will be finite rank operators with no operator norm less than 1, and this plus is the operation of taking the positive part in the space, in the target space y. And now we will have the following properties of this neural network. First of all, the d-star metric between f, the function f, and its neural network approximation will be bounded by 2 square roots of 2 norm f in this variation norm times x over square root of n. So we do have Monte-Carlo rates. And then if we also have a measure mu, probability measure mu with p finite moments, then we also have a convergence rate in the Bochner space LP mu, but this Bochner space, the target space in the Bochner space is now that completion of y with respect to the d-star metric. And these are the same rates that we had in the scalar case, save for this annoying square root 2 here, which might be either a technicality or a small mistake somewhere in the proof, or a small typo somewhere in the proof. Now these moments, they were not present in the scalar valued theorem, but I think they should be, and maybe Stefan could correct me if I understood something wrong in his papers. And then again, we have this norm f, and we have the square root of n. So we basically reproduce the same results, but we had to assume a few things, quite a few things on the target space y. Okay, that brings me to the conclusions. What have we done? We have generalized these variation norm spaces with ReLU activations to networks that take values in some Banach space. And this Banach space had to satisfy quite a few assumptions. But under these assumptions, we proved inverse and also direct approximation rates, which I didn't talk about. And we obtained, there are inverse and direct approximation theorems, and we obtained Monte-Carlo rates. Our results were obtained for these generalized ReLUs, but they hold also for any weakly star continuous activation function. Now we saw a major limitation. This weak star continuity of the nonlinearity is not fulfilled by a function that seems rather natural that we would like to have, the ReLU. The question here is it a technicality that we had to use the weak star topology everywhere? And remember, we did it in order to have the right duality between continuous functions and random measures. Can it perhaps be done differently so that we do not need to switch to the weak star topology, and then we will not have all these problems? This is a question, and of course, I would also like to think about more interesting architectures than just 2-layer neural networks. And in the scalar valued case, there is work on various architectures. So this is something I need to think about later. So the preprint is online on arXiv if you're interested. And with that, I'd like to thank you for your attention.